Hello, hello. Let's start our worksheet Bohr. Ozone, O3, absorbs light with a wavelength from about 100 nanometers to 900 nanometers. One of these absorption bands is termed the Hartley band with wavelengths between 200 and 300. Term the energy of a photon of UV as light. Okay, so I'm looking for energy, so my first thought is E equals HV. But I have wavelength, darn it. And as soon as I see 250 nanometers, I change it to 250 E negative 9 meters. This equation I'm going to have to use a little bit later. So I'm going to use this one first. Frequency equals c over lambda. C is the speed of light, which is given to us on our equation sheet, and 250 e negative 9. I'm going to grab my calculator. 3e8 divided by 250 e negative 9. And I have 1.2 e15 hertz. And that's my frequency. So now I'm back. Sorry. So E equals H nu. And again, the weird part about this is we have so many given numbers that we have to get comfortable with. 6.626 E34, H is given, and C is given on your equation sheet. Times frequency. I just want to point out again that this has to be in meters, or my power of 10 gets messed up. So frequency was 1.2 E15. Whoops. So 6.626 E negative 34 times 1.2 E15 is 7.95 E negative 19 joules. And that's the energy of a photon, which notice isn't very much because just one little bundle of energy, one little light thing that exists for a little bit. Determine the frequency of the same photon of UV light. And the energy determine the frequency. So first we found the energy, we also found the frequency. There's that answer right here. Determine the energy of a mole of these photons. So this was the energy for one. So 7.95 E negative 19 hertz times the number of particles in a mole, 6.02 E23. 7.95 E negative 19 times Avogadro's number. I'm going to write down all the numbers and I'm going to round it 478,590. You know we need 3 sig figs here. So we'll go 4.79 E. Oh my goodness, I can't count commas. Still 4.79 E5 joules. The energy to break a bond in O3 is 110 kilojoules. Per mole. Do the photons in the Hartley band have enough energy to break 1 mole of these? Energy to break a bond is, okay, so kilojoules per mole. So this is going to be 101,000 joules per mole. That's going to be joules per mole. 101,000 joules per mole. So I'm going to, this one right here was 478,000. So see how this was 478, 590? Does it have enough energy to break 1 mole? The answer is yes, because 478, 479, I suppose is what I should stick with. 479,000 is greater than 101,000. All right. Unit of measurement that's often used in spectral analysis is wave number. That's new for me. Wave number is given the symbol Bohr. And it looks like average velocity, but it's average frequency. It has the units of centimeters to the -1. Well, wave numbers are not a unit of energy. They're directly proportional to the energy of a wave and inversely proportional to wavelength. Red light, which is considered low energy visible light, has a wave number between that and that. While UV light, which is higher energy, has a wave number between that and that. Determine the frequency in hertz of the red light at 15,000 centimeters -1. Are not a unit of energy. They're directly proportional energy. Like, Determine the frequency in hertz. To do so, multiply by the speed of light in centimeters per second. This is what I get. So we have 3.00E8 meters per second. I was trying to figure this little dog out, and I got to get it to centimeters per second. So I'm going to rewrite this. This should look familiar to you now. 1 meter is 100 centimeters. So I'm going to get 3E10. And that's going to be centimeters per second. And it says to determine the frequency of hertz per light. Okay, so I'm going to take this and multiply it times 15,000. And that's centimeters per second, and I just like to write that as centimeters over 1. And notice how these will cancel, and my units will end up being 1 over seconds, which is seconds to the negative 1. 3E10, can you tell I'm happy I have my calculator back? Times 15, 1, 2, 3, 4.5, E14. Determine the amount of energy, and that is the frequency. The energy in joules for the same red light. Energy equals H nu, 6.626 E negative 34 times 4.5 E14 equals my previous answer times 6.626 E negative 34. I get 2.98 E negative 19, 2.98 E negative 19 joules. Determine the frequency in hertz of UV light at that. So again, I'm going to use this thing, kind of weird. Whoops, multiply by the speed of light in centimeters negative 1. So we found out that it's 3E10. So 39,000 centimeters negative 1. So 39,000 times, we're using the same thing we used up here. Whoops, not that. Times the speed of light in the unit they want us to use. So 3E10 in centimeters. 39,123 times 3E10. And 1.17 E15, and that's going to be hertz over seconds to negative 1. And that's it. To the amount of energy, same thing. E equals H nu, 6.626 E negative 34 times 1.17 E15 equals that same number times my old friend. 6.626 E negative 34. And I have 7.75 E negative 19. Determine energy in joules. Electromagnetic spectrum is wavelength and energy inverse. So I remember wavelength is always, I always think that's wavelength, and that's a weird shape, and that's proportional, but it's inversely. It doesn't really help. But wavelength is inversely proportional to pretty much everything. The electromagnetic spectrum, what is ratio of frequency and energy? Directly proportional. Which is higher in energy? X-rays. Which is higher in energy? Visible light or ultraviolet light. So I gave you that little spectrum thing where, remember, gamma is the most. And just think about how harmful it is, and radio is the least. And remember, wavelength is the opposite of it, and frequency and all that stuff is the same. Which is higher in energy, infrared or gamma rays. And that's that little dog. And that's it. Doodles.